Episode: Culled Data, Scene Graphs, and Search. Culling data using scene graphs and search algorithms. We have been through a lot of techie episodes, and this will be the last of the techie episodes. At least the last of the deep dive techie episodes. In this episode, let's talk about culling data, using scene graphs, possible search algorithms, and leveraging open source. Sometimes optimizing can be removing things. This is called culling. Culling them is important. Culling data will be a great optimizer. It can be deleting things. It can be discarding partial or entire processing of data. Doing so is an obvious win for performance optimization. Not doing something, culling something, is faster than doing something that you could have not done. A powerful way to reduce active data from being processed is to cull it from the processing list. Identify things that can be ignored for any given update or refresh cycle and cull them from the update process. Save the processor or process or network, the cloud, cycles and operations. Maybe even save some memory in the process. Another way to cull data is to simply group it into blocks that should be processed only when they are in view or are active. Data can be grouped into sections, so only specific areas or sections need to be processed at any given time. Grouping data is sometimes a better way to cull data. And finally, organizing data into large areas or sections that can entirely be ignored, not just culled in real time at runtime, will save an insane amount of performance and memory. An example of scene graphing might be found in a car racing game. Imagine the racing car track is broken into many sections of streets and buildings like blocks, and each one is containing a bunch of model meshes and textures, as in the images or the objects that you will see as you drive down the road. Based on where the player camera view is, looking from the car's vantage point, the street and building sections in front of it, to its left and to its right, should be actively in memory and being processed. But the rest of the huge racing track does not need to be processed at all. It may not even need to be in memory. Scene graphing and culling offer immense performance savings. As an aside, let's talk about hiding scene graph section loading for areas that are not in memory when you need them. I have seen and used occlusion as a way to buy time, to asynchronously load levels and assets behind the scenes, so the player had no idea that things were loading in anticipation of where the player was headed towards. Even popular games like the World of Warcraft have used big entry areas or entryways for castles and new areas, so the player would enter a big tunnel that required the player to move around some kind of occluding wall, cliff, or massive door before they could see the new area. As they transitioned between those areas that they could not see, the new area was being loaded. The game loaded the new area while the player was in the airlock transition corridor of control. Airlock occluded asynchronous scene graphing is an invaluable way to make a world seem entirely seamless and never require a loading screen, at least not during gameplay. I have found two scene graph methods that work the best for me. One was just a simple two-dimensional array, like a Cartesian plane on graph paper, that represented area section blocks of the world, where each map square node on that graph paper or section would contain lists that pointed to relevant level or area section data blocks. It assumed that each area represented an equal physical space, a la a simple 2D Cartesian map grid. I also, however, have used an octree, which had section lists as well, which would point to level section data blocks. However, the octree I used to support varying density areas so that sparse areas would be one pointer to a huge area and yet the data was small, whereas very dense areas like the racetrack inner city might have a whole bunch of little areas with concentrated blocks or lists of data. The idea again is that you can save lookups and only load the amount of data you need based on the areas you're looking at. And likewise, your field of view, how far you could see, can actually be greater based on lower detail or lower fidelity. Finally, organizing data into large areas or sections that can entirely be ignored. That's not just cold in real time or runtime. Like I said before, it will save an insane amount of performance and memory. Let's continue on a different area. There are many search and find and maze traversal algorithms and approaches. Your search algorithms can take a long time and they can be significant impact to your product's performance. Search algorithms are not all created equal, and different situations may justify different algorithms. I will just say this. Starting from point A to find point B is slow. Starting from point A to find point B while also starting from point B to find point A is faster. The idea is that each search has a probability of incorrect maze traversals that will require some level of backtracking. Therefore, two searches should, more often than not, result in fewer backtracking incidences. And thus, searching from both the start and the end of the maze should be faster than merely starting from the beginning and searching for the end of the maze. Searching from both the start and the end is a known and established search algorithm. It is called A*, A*, or A-star, STAR. Of course, there are always canned and pre-recorded paths, but that is very script limited and time intensive. So in general, I recommend, other than for staged theatrical visuals, use an A* search algorithm. Ever since working with large corporations, open source became a thorn in everyone's side. Open source leverages the world of engineers and innovators. It sounds like an awesome and great idea. In fact, it is, in the right situation. Open source provides free progress and capabilities. Open source includes, however, bugs and problems. Open source has constrictive licensing. Open source may not include all of the source, potentially being black hole binaries. They could be buggy. They could contain a virus. They could have unacceptable memory or performance impacts and demands. Well, that's the last episode on optimization. I hope once again there were some nuggets of value to you and to your projects.